Hello, welcome to the second lecture of convective heat transfer. Today we will be discussing about balance of total energy. In the previous lecture I have dealt about different modes of heat transfer and we have seen that what is the essence of convective heat transfer in that. Few applications of convective heat transfer also we have introduced over there. Today let us see the mathematical formulations related to convective heat transfer. So, first we will be dealing about energy equation. So, as outline of this lecture we will be understanding what is the balance of energy from the first law of thermodynamics. So, as thermodynamics is prerequisite of this course, so all of you know that what is the first law of thermodynamics. From there we will be finding out the balance of energy, term by term we will be evaluating the balance of energy. Next we will appreciate dealing of body and surface forces. So, what are the basic differences of body force and surface force we will be discussing, as well as we will be subtracting mechanical energy from the total energy balance and find out the thermal energy balance. Towards the end I will be showing you internal energy and enthalpy form of thermal energy balance equation. So, all of you know what is internal energy and enthalpy, as thermodynamics is a prerequisite of this course. So, we will be expressing the thermal energy balance equation in the form of internal energy as well as enthalpy. So, to begin with, let us start how to do this total energy balance equation. We will be starting from a closed system. So, here I have shown a closed system. You see this is a closed system bounded by a boundary here I have shown by a dotted line, and the system is having mass m. Okay. At any arbitrary surface, if you draw the surface normal, that is n cap, and let us consider, as we are dealing about the energy balance equation, let us consider through that surface q bar amount of energy is being released. Now, all of you know, as per the first law of thermodynamics, for a closed system we can balance the energy in transit as well as the energy in storage. So, first let us talk about energy in storage. For this system, let us consider that energy is capital E. So, energy in storage will be changing in the form of dE dt. Okay. So, in the left hand side we are having storage energy change with respect to time, and in the right hand side we have all the energies which are in transit. So, transit energies can be in terms of heat transfer q dot as well as the work transfer w dot. If you take the sign convention in a proper manner, you will be finding out they are opposite in nature, and if you just reverse the sign convention, these signs will be changing, but overall the equation can be written in this fashion. Okay. So, we have actually equated energy in transit and energy in storage and energy in transit over here. Okay. Next, let us see what is this energy in storage inside this system, capital E. So, this capital E will be actually summation of the internal energy E, small e, and its kinetic energy. Here ui is a vector. So, if we are talking about a 3-dimensional plane, ui will be having 3 different components. Okay. So, here you see E I have mentioned as internal energy. Now, here as it is a finite volume, so we have to consider about the average internal energy of this system. So, here I have dealt with E star. So, star symbolizes the average specific internal energy. Okay. Similarly, ui star is actually average velocity. Okay. Next, if you try to do the temporal derivative or derivative with respect to time of this term E, then you will be getting dE by dt or ddt of E is equals to m. Mass is not going to change for this control volume or for this control system. So, you will be finding out m is coming out and ddt is remaining over the term inside this brace E star plus half of ui star into ui star. Okay. So, here what we have done, we have found out what is the balance of energies in a closed system, and energy in storage we have found in this fashion. Next, let us see what about energy in transit. First, we will be discussing about energy via heat transfer. So, let us consider that for a small amount of surface, a very small infinitesimal amount of surface over here, which is having surface area dA, through that dq dot amount of heat energy is being released, okay, and that energy is being released in any arbitrary direction. So, for finding out the energy balance, we need to find out that what is the component of the energy being released normal to the surface dA. So, what we have done over here, dot product of small q bar, which is over here, okay, dot n cap is the normal direction, okay, of the infinitesimal small surface over here, n cap into dA, that will give us the account of del q dot, right. Then for finding out the overall q dot, which is being released from the overall surface of this control volume, we need to integrate this term whatever we have got for this infinitesimal small area over here for the overall area, surface area. So, here we have done the surface integral of that term, integration of S of this term q dot n cap into dA, okay. Here at this moment we have applied divergence theorem from vector calculus. So, you can find out over here, as per divergence theorem, surface integral can be converted to volume integral, okay, and after this conversion the inside term will be converted to divergence of q into dV, del q into dV, okay. In a similar fashion, here what we can do, del q we can write down as average property, as I have shown you in the previous slide for small e and ui, okay. So, that average property can be once again represented as q star, which can be taken out from the integration because it is averaged, okay. So, if you take out this del q bar out of this integration by giving this star, then integration of dV over the volume will become total V. So, what I can write down, minus del q star into V. So, total heat energy will be coming as minus del q star into V, right. Next, let us see the work transfer, which is another form of energy in transit. So, we can have the work transfer as two parts. First one is work transfer due to body forces, so W dot O, and work transfer due to surface forces, which is W dot S, right. So, here let us see that how first the body forces can be evaluated. So, work done by body forces W dot O can be written as integration of rho dV g dot u bar, okay. Here g and u bar, these are vectors, okay. So, g is actually the body force acceleration term, okay. In case of a gravitational problem, so you can find out this g will be equivalent to 9.81, okay. So, there can be some other accelerations also apart from gravitational acceleration. So, that is why we have kept this one as vector over here, depending on the magnitudes of different directional accelerations, this will be getting components, okay. So, work done by body force can be written as rho dV g dot u bar, okay. By the way, this negative sign is very important. Why? Because we have considered that if we have done work on the system, that is negative, and if the system is doing work, that is actually a positive one, okay. So, here you see we have found out that this term after integration once again can be averaged out. So, this term we have averaged out, rho and gi will be coming out as usual, ui we have averaged. So, this is ui into ui star, and then this will be becoming v, integration of dv will be becoming v, right. What about surface forces? So, in case of surface forces W dot S, we can write down that one as surface integral of S n cap. Now, this S n cap is actually surface stress vector, okay, into dA dot u bar, okay. So, this surface stress vector can be also expressed in terms of stress tensor. So, let us see what is that SI, which is the component of this surface stress vector. So, SI can be written as tau Ji into Nj. Here J is the dummy index which will be running from 1 to 3 or let us say x, y and z coordinates. Okay. So, this SI is equals to tau Ji into Nj. Here this tau Ji is actually the stress tensor. Okay. Now, if we further simplify this term, work done by surface force, then we can write down this S n cap dA into U as Ui into Si into dA. So, we are dealing here component wise, ith component if we write down, and then if we do the integration over the surface, then we will be getting the total work done by the surface forces. Now, here already as I have showed that SI can be related to stress tensor tau Ji. So, I am writing down over here SI equals to tau Ji into Nj following this relationship. So, you can get W dot S can be written as surface integral of Ui tau Ji Nj into dA, right. So, we have got some sort of idea about work done by body forces as well as work done by surface forces. Now, if we once again apply on this surface force the divergence theorem from vector calculus. So, this was surface integral, we can easily convert that one into volume integral. So, here you see from surface integral to volume integral we can write down del xj of Ui tau Ji into dV. So, this was on dA, now it will be converting to dV. Okay. So, here we have got once again some problem which can be averaged out. Okay, just like the previous cases. So, here what we have done the volumetric average of this one, and this term we have written as star term taken out of the integration. So, you see del Ui tau Ji del xj or del xj of Ui tau Ji has been written as star terms, which is volumetric average of this term multiplied by volume whenever we have taken this term out. So, it will be integration of dV only over the volume. So, it becomes V. Okay. So, this term we have got for the work done on the surface forces. So, till now we have seen that energy in transit can be written as Q dot, which is simplified in this fashion, W dot which is having two components, W dot O which can be simplified in this form, and W dot S which can be simplified in this fashion, surface forces. Okay, work done on the surface by the surface forces. Okay. Then let us first add both the terms of the body forces and surface forces. Okay. So, W dot as we have already shown will be equivalent to W dot O plus W dot S. So, we can just add the previous two terms. So, that means this term as well as this term. So, you can get this minus of this. Okay. So, first one is for the body forces, second one is for the surface forces. Okay. Now, if we substitute this body and surface forces in total energy equation along with the Q dot, which already I have simplified into a vector form. So, then we will be getting, you see this left hand side was actually your energy storage, rate of change of energy storage. Okay. So, and in the right hand side first term is coming from capital Q dot which was heat transfer. Okay. And this term is coming from your work transfer. First part is actually work done due to body force and second part is actually work done by the surface forces. Okay. Now, let us take some simplifications. So, first what we have done, this whole equation I have divided by V, that means volume. So, if you do so, m by V will be becoming your density rho. Here also V and V will be cancelling in the first term in the right hand side, second term in the right hand side also V will be cancelling, and here also the V can be cancelled if I divide it by V, the whole equation. Also, let us take the limit of V tends to 0, that means very infinitesimal volume. Okay. So, from control volume now we are moving to the infinitesimal volume problem. Okay. So, if we do so, then you can find out this m by V will be coming as rho, rest terms will be remaining same. Now, as we have taken the limit V tends to 0, average property can be now written as simple properties. Okay, so I have dropped the star terms over here and written in terms of simple terms. So, E has been converted to E star has been converted to E, Uy has been converted to Uy star has been converted to Uy, and so on. In the right hand side, after dropping the V, every term is coming as simple term, and also we have dropped the star due to this limit V tends to 0. Okay. So, from this equation, by dividing V throughout in the left hand side, right hand side, and by taking the limit, we got this equation. Okay. Now, so this equation is very important, this last equation is very important, this is actually balance of total energy equation. Okay. Left hand side we are having a rate of change of energy in storage, and in the right hand side we are having account of energy in transit. Next, let us see that what are the balance of mechanical energies, because we know that if we have to find out the thermal energy balance equation, this will be simply total energy balance equation minus the mechanical energy balance equations. Okay. So, we have already found out the total energy balance equation, let us find out the mechanical energy balance equation in order to get the thermal energy balance equations. So, for mechanical energy balance equation, from our mechanics we know that Cauchy's equation of motion gives us this type of equation. So, in the left hand side we are having rho into ddt of Uy, okay, which is equivalent to your inertia. Okay. Then in the right hand side we are having the body force related term, okay, rho into Gi. Gi is the acceleration in a particular ith direction, plus this is due to surface stress. Okay. So, del xj of tau Ji, right. So, this is your Cauchy's equation of motion, all of we know this one. Next, if we just multiply this equation by Uy, okay, then you will be finding out this can be written as rho into ddt of Uy into Uy by 2. Why? Because if you just multiply Uy over here, this will be becoming Uy into ddt of Uy, which can be written as half of ddt of Uy square. So, here I have taken half inside, so it can be written as rho ddt of Uy square by 2. Okay. In the right hand side, this will be simple, very simple, rho into Gi, and I have multiplied by Uy. So, rho into Gi into Uy, and then this term will be Uy into del xj of tau Ji, which can be written as this two term. We are actually using over here ddx of u into v is equals to u into ddx of v plus v into ddx of u. So, here you see del xj of Uy tau Ji can be written as tau Ji del xj of Uy plus Uy into del xj of tau Ji. Okay. So, if you just alter the sides, then you will be getting Uy into del xj of tau Ji will become del xj of Uy tau Ji minus of tau Ji into del xj of Uy. Okay. So, this simplified form we have got from the balance of mechanical energy. Now, if we subtract this mechanical energy balance equation from the previous total energy balance equation, okay. So, that means if we subtract from this one, okay, the total mechanical energy balance equation, this one, okay, then we will be finding out our balance of thermal energy. Okay. So, after subtraction you will be finding out some terms will be dropping out from both the sides, especially this term will be equivalent to your previous this term. So, these will be cancelling out. So, eventually you will be finding out that we are having in the left hand side rho of ddt of small e, and in the right hand side we will be having minus of del q plus of tau Ji into del xj of Uy, because this term will be cancelling with this term, right. So, you can find out finally the thermal energy balance equation comes as this one, rho of dE dt equals to minus of del q plus of tau Ji into del xj of Uy. Okay. This is very important equation. So, this equation we will be further simplifying in terms of getting simplified forms. So, let us see first this last term. In the last term you see we are having tau ji. Okay. So, let us see what is this tau ji or stress tensor. So, if we see the stress tensor from our fluid mechanics knowledge, we can write down that stress tensor is nothing but having two part, hydrostatic part as well as deviatoric part. Okay. So, hydrostatic part of the stress tensor is minus P del ij, and deviatoric part I can write down as pi gi. You see this was tau gi, this is also pi gi. So, let me give you one example of this type, what is this hydrostatic part and what is this deviatoric part. Let us say the stress tensor is having this fashion. So, tau ji is having 9 components. Let me give you example with 9 different values which will be easier to understand. So, for simplicity let us take 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay. So, in 3 by 3 matrix, okay, for 3 different direction x, y and z direction, we will be getting tau ji like this. Okay. Let us say this is some arbitrary stress tensor. Now, for the first part, hydrostatic part, we will be considering only the diagonal terms. Okay. So, hydrostatic part we can write down. So, tau ji hydrostatic part. Okay. This can be written as, this is actually having only the diagonal terms, rest terms are 0. So, this can be written as this 0 0, then 0, then 0, then 0 0, only the diagonal terms will be remaining. Now, what is this diagonal terms? Diagonal terms will be here from your original stress tensor. If you see the diagonal terms, add those and divide it by 3. So, here what we get 50 plus 10, 60 plus 90, 60 plus 90 is equals to 150. So, 150 by 3 if you do, it is becoming 50. Okay. So, here all the terms will be equivalent to 50. Right. So, we have got hydrostatic part is having only the diagonal elements, or we can say wherever I is equals to j. Okay, in this tau ji, there only the hydrostatic part exists. Okay. So, this tau ji hydrostatic we can write down as tau I for all i's divided by 3. That means tau 1 plus tau 2 plus tau 3 divided by 3. So, if you do so, here you will be getting 50 50 50. Now, to get the deviatoric part you have to subtract this hydrostatic part from your stress tensor. Okay. So, we will be finding out that our deviatoric part becomes tau ji deviatoric part will be becoming tau ji minus of tau ji hydrostatic. Okay. So, hydrostatic part we have only got the 50 terms in the diagonal. So, here we will be getting rest terms as usual. So, 20, 30, here we had 40, this term will be changing 60, 70, 80 and the diagonal terms will be changing. Now, at the first place we had 10. So, 10 minus 50 it will be becoming minus 40. This term will be becoming 50 minus 50, so that means 0, and this term will become 90 minus 50 which means 40. So, this becomes my deviatoric part. Okay. So, in this fashion the deviatoric part can be obtained. So, here also we are having these two components, hydrostatic part of the stress tensors as well as deviatoric part of the stress tensors. Now, let me show you further. So, if we multiply this tau ji with del xj of ui, why I want to do so? Because in my last part of the balance of thermal energy I had tau ji into del xj of ui. So, let us see what is this term. So, here you see if I multiply this, then I will be getting tau ji into del xj of ui, which is the last term of my thermal energy balance equation, is becoming the hydrostatic part multiplied by del xj of ui and deviatoric part multiplied by del xj of ui. Okay. Now, for further simplification what we can do, this del xj of ui for the deviatoric part attached to the deviatoric part, I can write down in two terms, which is nothing but dij plus rij. Here I am saying this dij and rij's are deformation tensors and rotational tensors. So, how I have written this dij and rij? Dij is actually half of del del xj of ui plus of del del xi of uj, and here the rotational tensors are having equal terms, but in between we are having just the change of sign. So, if you just add these two, so you will be finding out the last terms will be cancelling, and half of this plus half of this will become del del xj of ui, which is nothing but this part over here. Okay. So, this del del xj of del del xj of ui we have written dij plus rij, deformation tensor plus rotational tensor. Okay. Next, let us see further. Now, this rotational tensor rij, whatever I have shown you over here, is actually antisymmetric. Okay. So, we can write down pi ij of rij plus rji is equals to 0. So, I can drop rij term from the equation. So, we get rest things same, only in this place where we had earlier tau ji into del del xj of ui, I am writing pi ji into dij. Okay. One reason of not writing the next term is that rotational tensor is antisymmetric, right. In a similar fashion, now let us go for some common fluids. So, we know that fluids can be of different types, and the most common one is Newtonian fluid. So, for Newtonian fluid, this pi ji, this deviatoric stress tensor, can be written as 2 mu dij minus of 2/3 of mu of del dot u, divergence of u into Kronecker delta. So, delta ij. So, here you have two different things. You see this for this Newtonian part, we are having viscosity coming into consideration, mu or viscosity coming into consideration. Now, if we multiply this one by dij, because dij into pi ij we are getting over here. So, then we will be finding out this becomes 2 mu dij into dij, once again we have multiplied, minus of 2/3 mu into del dot u into dij into delta ij. So, this is actually Kronecker delta. Now, if we proceed further, as per the delta operator or Kronecker delta properties, we know that dij into delta ij will become dii. Okay, because rest terms will be becoming 0. For this delta ij, whenever I and j they are not equal, this will become 0. Okay. So, this pi ij into dij will be changing to 2 mu dij into dij minus of 2/3 mu into del dot u into dii due to this Kronecker delta property. Now, from fluid continuity we can write down that this dii is equals to del dot u. Okay. So, after simplification we get that pi ji into dij is equals to, this term will be remaining as it is, minus 2/3 of mu into del dot u whole square, right. Okay. But now let us define this whole term pi ji into dij, whatever we have got over here, as a new term viscous dissipation phi. So, we are calling this one as viscous dissipation phi. Okay. Now, if we just give all the terms back in our thermal energy balance equation, you see left hand side remains same. So, your energy in storage, rate of change of energy in storage, and then right hand side in place of the stress part, okay, tau ji into del del xj of ui, I am writing minus p del dot u, this is coming from the hydrostatic part, and this then plus phi, which is nothing but viscous dissipation coming from the deviatoric part, right. So, this form we call as internal energy form of thermal energy balance equation. Okay. Here E is the internal energy. Next, let us see what are the other types, other forms. So, here let us try to replace this E by H, which is nothing but enthalpy. We are trying to see the enthalpy form of the thermal energy balance equation over here. Now, all of we know that H from thermodynamics, enthalpy from thermodynamics can be written as E plus P into V. E is the internal energy, okay, and V can be written as 1 by rho, specific volume can be written as 1 by rho. So, H becomes E plus P by rho. Now, let us do the derivatives. So, if we do ddt of E, we get ddt of H minus of ddt of P by rho, okay, and this if we multiply by rho over here, then we can get this rho is coming in front of all the terms, and this term can be now written as ddt of p into rho by rho plus of p by rho into d rho by dt. Okay. Now, from continuity we know that 1 by rho into d rho by dt is equals to minus del u. So, these terms become minus of p into del dot u. Okay. So, we have got minus of p into del dot u over here. Okay. So, we have actually found out rho into d dt in terms of rho into dh dt over here. If we substitute this in that internal energy form equation, we will be finding out that in place of dE rho into dE dt, we have written this term in the internal energy balance equation. So, you have got in the both side same term which we can cancel out. Okay. So, finally, we get that rho into dH by dt is equals to this will be coming in this side. So, plus dP dt and viscous dissipation will be remaining over there. So, this form is actually balance of thermal energy in enthalpy form, right. So, let us summarize today's lecture. So, what we have done, we have described the balance of total energy, okay, in a closed system. So, this was the equation. Finally, we have got derived balance of thermal energy in terms of stress tensor. So, we have got the stress tensor over here, okay, this was the final form. We have presented the viscous dissipation phi for a Newtonian fluid, and we have simplified that viscous dissipation in terms of thermophysical property mu. So, this looks like that. Okay. We have casted the thermal energy balance equation in internal energy form, as well as we have shown that as enthalpy form. Okay. So, let us test whatever you have understood in this lecture. Let us test your understanding. So, here I have actually I will be giving you two rows. In the left hand side of the row, we will be finding out some parameters which I have already discussed in this lecture, and in right hand side you will be getting the simplified expression of the parameters. You have to match one by one in that. So, let us see the options we are having. So, the options are like this. Left hand side we are having w dot o, w dot s, q dot, phi and dij. I think all of you know the usual meanings of this left hand side terms. In the right hand side we have jumbled up things. So, you have to match up. So, please take your time to read this one and then arrange. So, I think the final answer will be coming like this. All of you have got the correct answer. So, w dot will be coming as this one, which we have already shown. W dot s will be coming out this one. Okay. Q dot is this one. Finally, viscous dissipation phi is coming out like this, where we are having square over here. Dij will be coming out like this. Okay. So, I want to thank you for listening this lecture. Please visit our next lecture. There we will be discussing about different forms of thermal energy balance equations, and if you are having any question, please post us in the discussion forum. Thank you very much.